All right. So today we are going to talk about the conservative forces and potential energy. So what is conservative force? So conservative force is a force for which work done by that force or against that force does not depend on the path followed. Okay. So what is a conservative force? It's a force. It's a force. I'm sorry. It's a force for which work done is independent of the path followed. Is independent of the path followed. Okay. So for an example, let's consider some object and let's suppose there is only a conservative force acting on this object. Okay. So work done by that conservative force or work done against that conservative force to move this object from this position A to any other position, let's say B here. Okay. It does not depend on the path followed. So when we move this object from A to B, so you move it along this path, you move it along this path, or you move it along any path. Okay, so there will be work done to move it along this first path. Suppose it is W1. Work done to move it along second path is W2. Work done to move it along this third path is W3. So W1 will be equal to W2 and it will be equal to W3. So if there are only conservative forces acting on any body, then work done does not depend on the path followed. Okay, so what are some examples of conservative forces? Gravitational force is a conservative force. Okay, for an example, we'll see this. Gravitational force is a conservative force. Then the electromagnetic force. Electromagnetic force is a conservative force. Okay, all the fundamental forces are conservative forces. Then spring force. Spring force is also a conservative force. Okay, so this is clear. All right. So then let's talk about the non-conservative force. Okay. So if conservative force is a force for which work done does not depend on the path, that means what is non-conservative force? It's a force for which work done depends upon the path followed. Okay. So it is a force for which the work done depends on the path followed. Okay, so for a conservative force, work done only depends on the start point and end point. For non-conservative force, it also depends on the path followed. So what can be an example of a non-conservative force? One example is our frictional force. Okay, static friction, then kinetic friction or dynamic friction. It is an example of non-conservative force. Another example, it's again friction, liquid drag, okay, or air drag. Okay, so liquid drag is also an example of non-conservative force. Okay, so whatever force opposes the motion, that force is a non-conservative force. Okay, so for an example, let's consider a block like this kept on a floor, and initially it is at position A, and we are going to move it from this position A to B. Okay, so from A to B, from here to here. Okay, so now I move it from A to B like this. Okay, there will be some work done, right? Work done against what? The frictional force between this surface and the block. Okay, so there will be some work done when I move it like this. So now let's suppose I move it from A to B to C, and from point C again I move it back to the point B. So in second case, I will have to do more work against the friction, right? When I move it from A to B to C and from C to B, okay, back to the point B, I will have to do more work. So work done against friction. So work done against friction to move this block, okay, to move this block from A to B directly, work done from A to B is not equal to work done to move it from A to B to C to B, right? So this kind of force is known as a non-conservative force. What is the reason? It's because whenever you move this block against the frictional force, okay, you have to do work against the friction. Friction always opposes the motion. So you move it by larger distance, you have to do more work because friction always opposes the work. In contrast, if you think about the gravity, so let's suppose I move my cell phone, okay, from here to here, gravity will oppose me, but I move the cell phone like this, gravity will help me, right? Okay, so when I, so let's suppose I release it, it will fall down, okay. So if I move it like this, gravitational force is also acting in same direction as that of motion, right? But it will never happen in case of friction. So friction will always oppose the motion. Okay. So therefore, work done along different paths against the friction will be different. Okay. So let's see that the gravitational force is a conservative force. So this is the object. Let's suppose a ball, and I want to move this object from this point A to this point B. Okay. So this is the point B. So I will consider different paths. So this is first path, a horizontal distance from A to the point C, let's suppose, and from C to B. Then a straight line path, okay, a straight line path joining point A and point B. This is second path, and a curved path, which is like this. Okay, so this is our path 1, this is part 2, and this is path number 3. So now I want to prove that work done against the gravitational force to move this object, this ball, from point A to the point B for all these three paths is equal. Okay, it is equal. So if the work done is equal, then the gravitational force is conservative force. If work done is not equal, then it is not a conservative force. So what is direction of gravitational force? It will act downwards, right? So gravitational force acting on this ball is downwards. Okay, so F suffix g is the gravitational force, and it's equal to minus of mg. And now when I move it from A to C, what will be the work done? Tell me. Okay, so let's consider path 1. So total work done along path 1, I can say that it is equal to work done to move this ball from point A to C, WAC, plus work done to move this ball from C to B against the gravitational force. Okay, so what will be work done against the gravitational force when I move it from A to C? So because I want to find out work done against the gravitational force. Okay, I will take gravitational force F suffix g bar dot this distance AC bar. Okay, this will be work done by the gravitational force. I want work done against of it. So that will be what? Minus of this, right? It will be minus of this. So this is work done to move it from point A to the point C. Okay, so displacement is AC, and work done to move it from C to B, so from here to here, is equal to what? Minus of Fg dot Cv bar. Now work done against the gravitational force is, let's suppose, W1, so it is equal to minus of Fg, it is minus of magnitude of Fg, which is minus mg, multiplied by magnitude of this displacement from A to C, which is AC, multiplied by cos of the angle between them. And what is angle between force and this displacement? It is 90 degrees, right? It is 90 degrees. And what is cos of 90? Right? It is 0. So that means work done to move this ball from point A to the point C against the gravitational force is equal to 0. Okay, work done to move this ball from A to C against the gravitational force is equal to 0. Okay, and here it is minus of Fg. Okay, so it is minus of I will consider direction also. Okay, so minus of minus mg, and then you have Cb, this distance Cb, multiplied by cos of 0, right? Cos of 0. Okay, or what we can do is we will take only magnitude. Okay, only magnitude here, right? So now the gravitational force is acting downwards and its magnitude is mg, right? And I am moving this object from C to B. So how much would be the angle between this force and the displacement? 180 degrees, right? The angle will be 180 degrees. Okay, so it's not cos of 0, it is cos of 180 degrees. And what is cos of 180? Minus 1, right? Cos of 180 is minus 1. So minus minus will become plus, and suppose this much height is equal to h. Okay, so suppose this much height is equal to h. Okay, so Cb is equal to h. So what do you get? You get mg, you get work done to move this object. Okay, work done to move this object from A to C and from C to B is equal to what? mgh, where h is the height of this point B with respect to the point C or A. So this is clear. So then next I will move it along this path. Okay, next I will move it along this path. So see, this is point A. Now let's suppose this angle is theta. So I will resolve the gravitational force along two components, one along the path, one perpendicular to the path. Okay, so let's resolve it along two components. So this will be one component, this will be another component. So since this angle is theta, how much will be this angle? 90 minus theta. If this is 90 minus theta, then this angle is theta. Okay, so this angle is theta, right? So this component here will be Fg cos theta, and this component will be what? Fg sin theta. Just like the previous case, we have resolved the gravitational force along two components now. So this is component along this path, this is component perpendicular to the path. So what will be work done to move this object along this path? Okay, so similarly you can say W2 is equal to, what will be the work done? Minus of this component Okay, FG sine theta multiplied by the displacement, this displacement. Okay, AB multiplied by cos of how much? What angle?
90 minus theta.
No. See, we have taken this component. Okay, so we are finding work done against this component of gravitational force to move this object along this path. Okay, so consider this component, it is acting in this direction. This component is acting in this direction. We are moving it like this.
So 0.
180 degrees,
Yes, sir.
right? Component is in this direction towards left, you can say. Okay, it's inclined. Okay, but component is in this direction and I'm moving it in opposite direction. So how much is the angle? It's 180 degrees, right?
Yes, sir.
Okay, so this angle is
Yes, sir.
180. And similarly, plus you are doing work against this second component. How much will be that? So the second component acts in this direction and displacement is perpendicular to that. So work done is what? 0. If force and displacement are perpendicular, then work done against that component is equal to what? 0. Okay. Or if you want to write, you can write it as FG cos of theta multiplied by AB multiplied by cos of 90 degrees. So this is equal to 0. And what is cos of 180? Cos of 180 is minus 1. So minus and this negative sign becomes plus. Okay. And magnitude of FG is equal to mg, right? So mg multiplied by AB. Sorry, it is mg sine theta, right? Mg sine theta multiplied by AB. This is the work done. So is it equal to work done in first case? It's equal. Okay. See how. So this height is h. So in this diagram, you can say sine theta is equal to what? It is this opposite side CB, or you can say h divided by AB. So take AB on the other side. So AB sine theta is equal to what? It is equal to h. Okay. So we have AB sine theta, which is equal to what? H. Okay. So work done along this path is also equal to what? mgh. So you got it. Work done against the gravitational force to move this ball along this first path is mgh. Okay. Work done to move it along this path is also mgh. Work done to move this object against the gravitational force along this first path is mgh. Work done to move it along the second path is also mgh. And work done to move the object along the third path will also be equal to mgh. How? See how. So any curve, take any curve. I will take little bit simple curve like this. It can be broken down into n number of segments like this. One segment, second segment, third segment, fourth segment, so on and so forth. Okay. And now I'm breaking it down into n number of small segments. Okay. So now consider this much segment only. Let's call it dr, or let's call it dr1 bar. Okay. So I will move this object, this ball, along this path, and this path can be broken down into what? N number of small segments. So now when I move it along this path, okay, so this segment can be considered to be a straight line, right? It can be considered to be a straight line. Okay, so this is dr1 if you take sufficiently small segment. So I will zoom it. So let's suppose this is dr1. Okay, this is dr1 bar. So now you can resolve this dr1 bar, this displacement, small displacement, along two components like this, one along x-axis, one along y-axis. Okay, so let's call it dx and this one is dy. So work done to move the object, okay, along dr1 bar is equivalent to work done in moving this object along dx and along dy, right? Yes, no?
Yes, sir.
Okay, so work done in moving the object along dx, let's call it dx1 dy1. So work done to move the object against gravity along dx1, it will be equal to 0, right? So work done to move the object horizontally, because gravitational force will act downwards and the movement is like this. So this work done is equal to 0, right? So work done to move it uh, in this direction, okay, along dy1 will be equal to what? Mg multiplied by dy1. So work done to move the object from here to here, okay, along dr1 will be equal to what? Mg multiplied by dy1. Yes, no?
Yes, sir.
Okay,
Yes, sir.
just like we saw it here. So work done, see this inclined line, okay, so work done to move it along this inclined line is equal to work done to move it along this horizontal path from A to C plus work done to move it from C to B. So just like that, what I'm doing is I'm taking small segments of this curved path, and so if I take sufficiently small segment, I can call it a line, right? Then when you move it along this line, okay, dr, then work done to move the object along this inclined line is equal to what? We have seen that it's equal to work done to move it along the horizontal line plus this vertical line. Okay, so similarly you move it along, so what will be the total work done? So it will be sum of work done to move the object along dr1 bar plus dr2 bar plus dr3 bar plus dr4 bar, so on and so forth. Okay, and it will be equal to mg multiplied by height here is suppose dy1, height from here to here is suppose dy2, height from here to here is suppose dy3, so on and so forth. You add all those heights, what will you get? The difference between heights of these 2 points. Okay, so the total work done, so total work done along third path, okay, is equal to, you can say w3, it is mg multiplied by dy1 plus mg multiplied by dy2 plus so on and so forth up to plus mg multiplied by dyn, if you are breaking it down into n number of segments. And then you can take mg common, so it will be dy1 plus dy2 plus so on and so forth up to plus dyn. And if you add all of this, what will you get? You will get the total difference between heights of these 2 points, which is h. Okay, and therefore this will be equal to what? W3, it is mg h only. Okay, so work done against the gravity to move the object between any 2 points along any path will be equal. And what will be that work done? It is mg multiplied by difference between heights of those 2 points. So it means that the gravitational force is a conservative force, because work done against the gravity or work done by the gravity does not depend on the path followed. So this is clear, or is there any doubt? You can ask me.
Here, sir.
Yes, sir.
So let's suppose you take any conservative force. Okay. So work done against. So right now let's consider the gravitational force. Gravitational force to move an object from A to B. From A to B. So for small displacement, I can say work done by the gravitational force Fg bar dot dr bar. Okay, this will be what? Work done by the gravitational force. And I want work done against of it. So I will put negative sign, right? And if I want work done to move the object from A to B, okay, work done to move the object from A to B against the gravitational force, what will I do? I will take all small displacements like this. So I will break down the total displacement into n number of small segments and I will add it up. So this procedure is known as integration, right? This procedure is known as what? Integration. So it is integral of this thing, or I can take minus sign outside. So minus of integral of Fg bar dot dr bar, and from where to where? From point A to B. Okay. So it is equal to, we have seen it is equal to what? Mg h. Okay. And this can be written as, so what is mgh? So it is difference between heights of these 2 points. So I can say h is equal to h at B minus h at A. Okay. So h is equal to, so this is equal to mg h at B minus h at A. Okay. And this is equal to, I can say mg h at B minus mg h at A. So you can see it depends only on start point and end point. Okay. And this change in work done is known as the change in potential energy. It is known as what? Change in potential energy. So this term that we are getting here, so we call this increment in the potential energy of the object. Why increment? Because we are putting energy, okay, external energy, because we are doing work against a force, and for that we have to put energy in the system. Okay, so it gets stored in the system in the form of potential energy. So this is known as potential energy at the final point, and this is known as potential energy at the initial point. So this is gravitational potential energy at B minus gravitational potential energy at U. So integral from A to B, work done against the gravitational force gets stored as what? Gravitational potential energy of the object. Okay, so work done to move it from A to B is equal to what? Potential energy at B minus potential energy at A. So this is clear. So this is true for gravitational force, and it must be true because see, what's the special thing about the gravitational force? The work done does not depend on the path followed. That's why we can write. Okay, that's why we can define quantity like this. Quantity like potential energy, because the work done depends only on start point and end point. So it is true for all conservative forces that the work done depends only on start point and end point. It does not depend on the path followed. So it is true for all conservative forces. So this result will be true for what? All kind of conservative forces. Okay. So this is the relation between work done, or you can say conservative force, and potential energy. So for all conservative forces, so let's suppose Fc bar is any conservative force, okay, it's any conservative force. So this kind of relation will be true for any conservative force, because work done depends only on the start point and end point. So for any conservative force, work done against the conservative force Fc bar to move the object, okay, to move an object or a particle or a charge from some initial point A to some final point B. So it will be WAB, and that's equal to minus of Fc bar dot dr bar from A to B, the integral of Fc bar dot dr bar from A to B. And we can always define, if we have a conservative force, we can always define a quantity known as potential energy. Okay, so it only depends on the final point. See, this will be some function, this integral will be some function, right? And now let's suppose you get function called as u. Okay, so you will get u. So now you will put what? The lower limit and upper limit. Lower limit is what? Lower limit is the initial point, upper limit is the final point. Okay, so it is u at point B minus u at point A. So how are we convinced that we can define this potential? Sorry. So how are we convinced that we can define this potential energy? Because work done does not depend upon the path followed. It only depends on the initial point and final point. So that means we'll get a unique function. Okay, we'll get a unique function. Okay, which is known as the potential energy. So this thing is clear. Okay, good. So then this is one relation between the conservative force and the potential energy. Okay, so the integral of conservative force gives you potential energy. That means what will be potential energy, or what will be conservative force in terms of potential energy? If you remember the fundamental theorem of calculus, so what does the fundamental theorem of calculus say? So if you have some function f and g, okay, you have two functions f and g, such that dg by dx is equal to f. Okay, so f is what? It is derivative of g with respect to x. Then you can define, okay, if you take integral of what? If you take integral of f dx, what will you get? Let's say from point A to point B, what will you get? You will get g. So from some lower limit A to upper limit B. If derivative of g is f, then integral of f will give you g, because integral is what? It is antiderivative or antiderivative. For an example, okay, let's take an example. So derivative d by dx of sine x is what? It is cos of x, right? So now if I integrate cos x dx, what is integral of cos x? From some x equal to a to x equal to b, it is sine x. Okay, lower limit is a, upper limit is b, right? So you can put the upper and lower limits. Okay, so if derivative of sine x is cos x, integral of cos x will be sine x, right? So we can use this fundamental theorem of calculus. Okay, so we got this result, minus of fc bar dot dr bar, okay, from A to B is equal to what? ub minus ua, right? Or you can say it is some function u from what? A to B. lower limit is a, upper limit is b. So integral of this thing minus of fc bar, okay, integral of minus of fc bar is u. So what will be fc? So if there is only one component, so let's consider only one component. So instead of dr, I will just take dx. Okay, I will just take dx. Let's consider one dimensional force only. Okay, so integral of this is u. So that means what is minus fc? It is equal to du by dx, right? And that means what is fc? It's equal to minus of du by dx. Yes, no? This is the relation between a conservative force and potential energy. Conservative force and potential energy. So if you consider one dimensional relation, then the force is given by what? Minus of derivative of potential energy with respect to x, okay, or whatever direction you have taken, okay, you have chosen. All right, so now force is a vector quantity, okay. So in general it will have how many components? 3 components, okay. So in general force will have 3 components. So what can I say? So for x component of this conservative force, I can write it is equal to minus of du by dx. Y component, okay, y component fcy is equal to minus of du by dy, and the z component fcz is equal to dz, right? And therefore now how can I write the force fc bar? So it has 3 component, and now the potential energy, okay. So because we are considering 3 dimensions, the potential energy will be function of what? X, y, z. So in general potential energy will be function of x, y, z. So now when you take derivative of this potential energy with respect to x, what will you do with y and z? You will treat them as constants. You will treat them as constants, okay. So when you take derivative like this, it is known as partial derivative. You take derivative of potential energy with respect to x, you will treat y and z as constants. So this kind of derivative is known as partial derivative, and it is written like this. So this is called as partial derivative, okay. And with respect to, you will take x, okay. So this will give you what? This will give you the x component of conservative force, okay. So therefore multiplied by I cap, and then I can take minus sign common. So minus of this is known, this is called as dou, okay, or some people call it daba, okay, or you can just say partial. So partial u, partial x, or partial derivative of u with respect to x into I cap. This will give you the x component. Then similarly y component will be given by what? Minus of partial u, partial y, and the z component is given by what? Minus of, this minus sign is common in all, minus of partial u, partial z, okay. So when you take derivative with respect to z, you will treat x and y as constants. When you take derivative with respect to y, you will treat x and z as constants, okay. When you take derivative with respect to x, you will treat y and z as constants, and in short it is written by this symbol. So have you seen this symbol anywhere? Okay, this is known as the gradient operator or del operator. So it is written as minus of del operator acting on u, in short. And what does this mean? This means this thing. Okay, so you can put a bar on top of this operator. So is this thing clear, or is there any question? Is there any question? You can ask me if there is any question. Stable, unstable, and neutral equilibrium. So let's suppose you have an object which is under the effect of only one kind of force. Okay, so let's suppose you have an object which is under the effect of conservative force only. There are no non-conservative forces acting on the object. So you can define potential energy function for the object, right? So potential energy, let's draw a graph of potential energy with respect to the distance. Okay, so this is u of x. We are considering one-dimensional case only, and this is x. So the graph can be anything. Okay, so let's consider a graph like this, a straight line, then a graph like this, and a graph, sorry, like this. Okay, so let's consider these three potential energy functions. Okay, so here now, since the conservative force is what? It is derivative. So since the conservative force is equal to minus of derivative of potential energy with respect to x. So how much would be the force acting on an object if potential energy is like this? It is zero, right? What is the geometrical meaning of derivative? Slope of a curve. Right, geometrical meaning of derivative, we have seen this. Okay, it is slope of a curve, right? So here, if you take derivative, okay, so let me give you an example. You don't remember, we had discussed this. So let's consider position versus time graph. How much is velocity when graph is like this?
Zero, sir.
Zero, no? Right? If graph of position versus time is like this, then velocity, what's velocity? Is derivative of position with respect to time. Okay. If graph of position with respect to time is like this, then velocity is what? It is zero, because position is not changing at all. Okay, position is not changing at all, right? So if I consider a graph which looks like this, okay, so can you tell me at which points, this is again the position versus time graph, at which points the velocity is zero? At point C. And what about B? At point B also, because slope here is zero, slope here is also zero, right? If you draw tangent to the graph, what is the geometrical meaning of derivative? Okay, velocity is derivative of position with respect to time. And what is geometrical meaning of derivative? So geometrical meaning of the derivative is what? It is slope of the tangent to a graph. Okay, so if you draw a tangent at this point, it will be a horizontal line. And what is slope of horizontal line? Is 0. Slope of this line, okay, tangent at C, is also 0. That means velocity at B, velocity at C is equal to 0. Okay.
Yes, sir.
All right. So now you tell me the points where force is equal to 0. So here, what is force? So just like in this case, velocity is dx by dt. Here we are having the conservative force equal to what? Negative of gradient or derivative of potential energy with respect to x. Okay. Here also we have derivative. That means we are finding slope of potential energy, but we are finding negative of the slope. Okay. So if the potential energy is like this, the potential energy function is like this, that means force is equal to 0 everywhere, because this graph is a horizontal line. What is slope of horizontal line? It's 0. Okay, what is slope of horizontal line? It's 0. What is derivative of this thing? It's 0. That means derivative of this thing is also 0. So what is the force on an object whose potential energy function is like this? It looks like this. It is 0. So when force is equal to 0, we say that object is in equilibrium. Okay. So this type of equilibrium, it's equilibrium everywhere at all locations, right? Because at all positions the potential energy is same. So this kind of equilibrium is known as neutral equilibrium. This is known as what? This is known as the neutral equilibrium. Okay. So here the potential energy is, the slope of potential energy, it is 0 at this point. Okay. And it increases if you go towards left or towards right of this point. Okay. So this kind of equilibrium, this is known as stable equilibrium. Okay. And this kind of equilibrium, it's at this point. Stable equilibrium, it is at this point. Let's call it point A. Sorry. And let's call this point as B. So slope of sorry. So the slope of potential energy with respect to x is 0 here also, it's 0 here also. Okay. So that means if object is here at x equal to a, in this potential, then it has 0 force acting on it. That means it is in equilibrium. So this is known as stable equilibrium. This one is known as unstable equilibrium. Okay, why? The reason is, when you will displace this object towards left or towards right, what will happen? There will be a negative force acting on it. Why I am saying negative? So if you go towards left or towards right, what's happening? The slope is positive, right? And what is force? Force is negative of the slope. Force is negative of the derivative. Okay. So negative force means attractive force. Negative force means what? Attractive force. So if you move the object towards left or towards right, that means away from this point, what will happen? It will be pulled towards that point. It will be pulled towards that point. And that's why the object is in stable equilibrium. Okay. So if you displace it a little bit, it will again come back to the same point. Okay, and that's why we say the object is in stable equilibrium, right? And here, if you displace it, what will happen? So if you go away from this point, the slope is sorry, the slope is negative, right? The slope is negative. That means derivative is negative. So derivative is negative. Derivative of potential energy is negative, and you take minus of that. That means force will be positive. What force is there? It's a repulsive force. Positive force means repulsive force. So this is unstable equilibrium. Why? Because you displaced that object a little bit. There is repulsive force acting on it. So what will happen? It will be pushed away from that point. It will not stay at that point. If you displace object from this point a little bit, what will happen? There will be attractive force acting on it, which will restore the object at this point. Okay, so that's why we call this stable equilibrium. And here, if you shift object a little bit, what will happen? It will be pushed away from that point. It will never come back to that point. And that's why we call this one unstable equilibrium. So you got this? Yes, no? These are the potential energy versus position graphs of neutral, stable, and unstable equilibrium. How will you check? Given the potential energy function, how will you check whether the okay, so given a potential energy function, how will you check whether it is a stable equilibrium or unstable equilibrium? So we had done something like this. What is this thing called? Maxima or minima? You forgot maxima, minima? Okay, tell me, this is the minimum point or the maximum point of this potential of this function. Potential is minimum there or maximum there? Minimum, right? So this is minima, and slope here is 0. Okay, after that slope is increasing. So what is change in slope? Change in slope is positive because slope is 0 here. After that point, the slope is increasing. So if you increase the distance dx, what is change in slope? Change in slope is positive. Okay, and how do we find change in a slope? So slope is first derivative, right? Change in slope will be second derivative. Okay, so change in slope is second derivative. So if d2x, sorry, not x, our function is u. So if d2, sorry, so if d2u by dx square, second derivative, okay, you are finding change in slope. How will you find? So slope is du by dx, one derivative. It is change in u with respect to x, and you want change in this slope. So you will take one more derivative, d by dx. So that is d2u by dx square. So if the second derivative is positive, that means you are at minimum point of the function. Okay, you are at the minima. So then, okay, then it's a minima. And that means which equilibrium? It is, that is the stable equilibrium. Okay, and if d2u by dx square is negative, right? So here see slope is 0, and after that it's slanting down. That means slope is decreasing. It's negative. Okay, so change in slope. So this negative number minus 0 will give you what? Negative. Okay, so if change in slope is negative, that means d2x by dx square is negative, then it's a maxima of u, that is, it's an unstable equilibrium. Got it? Yes, no?
Yes, sir.
Yes, sir.